I was thinking about choosing a topic. I was going through the private applied ACS, looking at all the, oral exam topics. I'm like, all right, operations of systems, that looks like a good one. And I'm going through all the topics, and I was like, man, this is a lot of stuff. So I was like, okay, I'll narrow it down to maybe 2 or 3 topics. So I think I decided I was going to do like flight controls, electrical system, and then the flight instruments. And I was making that PowerPoint. I'm like, all right, man, this is still a lot of stuff. So we're just going to do flight instruments for this webinar today. So for those of you who don't know me, my name is Wesley Chin. I'm a CFI at Princeton Flying School. I've been teaching here since last October. I also did all my ratings at Princeton, so private all the way to CFI was done all of these airplanes here. I also just finished my sophomore year at the Rutgers Business School studying finance, and I also teach saxophone and piano. All right, so what we're going to talk about today, we're going to start off with the pitot-static system and then all of its associated flight instruments. Then we're going to go into the gyroscopic flight instruments. And then what I'd like to do, we're going to try something a little bit different this time. So after that content, we're going to pause for some Q&A, some questions there. And then I have a couple written test questions actually at the end that we're going to try to go through together. So even if you're not preparing for a tech ride, let's say you already have your cert, and it's still a good idea to go through some of these things once in a while just to make sure you're not forgetting all the things that you studied back then. So we'll kind of go through some questions, see what we remember based on the presentation, kind of talk about those things as well. All right, so we will get started here. We'll start off with the pitot-static flight instruments. So first thing, we're going to start off with a question for you guys. So the pitot-static system is connected to what 3 instruments? Does anybody know the answer here? Is it possible to even unmute yourself? Let's see. I'm not sure, but okay. Does anybody know what instruments connect to the pitot-static system? Oops. Oh man, I clicked it. All right. Too bad for me. So it's going to be your airspeed indicator, altimeter, and a vertical speed indicator, right? So we've got 3 instruments connected to that system. The information provided by these instruments is all determined by measuring the pressure of the atmosphere. And as we know, that decreases as you climb, right? So we'll talk about that in a little bit more detail later. But basically, the system gathers its pressure information from 2 primary sources, right? We've got the pitot tube, and we've got the static ports. So we're going to break down those 2 components first before talking about each individual instrument. So in our 172 training airplanes, we've got a heated pitot tube mounted on the lower surface of the left wing, and it's designed to measure the pressure of the air as the airplane flies through it. So we're going to call that ram air pressure. The location of the pitot tube is no accident either, right? It's located under the wing so that it can measure the flow of the air without any interference. And then also something to look for is on the back side of the tube, we've got this very tiny drain hole that actually allows any rain or water that's collected through the system to drain out and not go directly into your instruments there. So here's what it looks like in our airplane. We've got the pitot tube over here on the left side. There's your front opening. And on the back, there's that tiny little drain hole. So, during your pre-flight, you want to make sure that stuff is unclogged. All right, so additionally, our pitot tube can be electrically heated. Let's say you're flying in the clouds below freezing level. You do not want ice forming there. That can definitely block your pitot tube and prevent your associated instrument from correctly functioning. So we can turn on the pitot heat with your pitot heat switch, and the element is protected by a circuit breaker labeled pitot heat as well. So that's the first part of the system, right? And then the second is going to be your static port. So on our aircraft, we have an external static port on the lower left side of the forward fuselage. Here's what it looks like, located right over there. It's just a little circle with the hole in the middle there. And again, the location of this port allows it to measure the static pressure of the air, unaffected by the dynamic airflow around the airplane, right? So the pitot tube is measuring ram air pressure, and then the static port measures static pressure. So, before we were just talking about, let's say there's ice or something blocking the pitot tube. In that case, we can turn on pitot heat, and then boom, problem hopefully is solved, right? And we don't have the blocked system anymore. Let's apply that same situation, though, to the static port. So what happens if the static port is blocked? Can we actually do anything about that? So how there's pitot heat. Is there anything similar for the static port? Does anybody know?
There's an alternate static as well.
All right, there we go. There's an alternate static source valve right over here, right? So right below your throttle in the flight deck over here, we've got an alternate static valve. So if you pull that out, we're now supplying static pressure from inside the cabin rather than the external static port there. So definitely something useful. Again, if that external port is malfunctioning due to, you know, kind of water or ice in that pressure line there. All right, so yeah, the pitot tube and static port openings are all connected through different tubes that join into your pitot-static instruments. So if we take a look at this diagram, which you can find in Chapter 8 of your PHAC, Pilot's Handbook of Aeronautical Knowledge, this is kind of what it looks like, right? You've got your pitot tube, and you've got your static port, and all of the associated tubing that runs through your three instruments, right? Your airspeed indicator, vertical speed indicator, and the altimeter. So what do you guys notice about how these the static port and pitot tube is connected to these instruments, right? Does every instrument utilize both information from the static port and the pitot tube?
Only the airspeed indicator uses the pitot tube?
All right, you got it, Omar, exactly. So only the airspeed indicator uses pitot tube, right? VSI and altimeter actually don't rely upon the pitot tube. It's just directly from the static port. Awesome. So again, just for stating here, all three instruments actually connect to the static port, but it's only the airspeed indicator that directly connects to the pitot tube. Sweet. So now that we've kind of discussed the basics of the system, let's kind of dive into how each pitot-static instrument will actually work. If you're here, you know, preparing for a private check ride or getting ready, you know, for a roll exam, you're definitely not going to know and, you know, need to know in too much detail, kind of be able to explain each instrument, but definitely we'll talk about what you need to know, what you don't need to know, because again, a lot of stuff in the books that is good to know, but you're not necessarily going to have to memorize that there.
I have a question.
Yeah. All right. What's up, Alex?
The question is, does that drainage system from the pitot tube in the back of the pitot tube, how does that how does it affect the actual ram air coming in? Is that on a different level, or is it the same space? Because if there is a drainage out there, so that means that the ram air comes through and may not be measuring the true speed of the air coming through the pitot tube.
Okay, so I just want to make sure I'm kind of understanding. So again, if you look at the diagram here, right, it's all entering the ram air pressure here, but there's that just tiny drain hole in the back. Yeah. So as long as that's anything's coming out of there, then there wouldn't be anything affecting the pressure going in. So I'm not sure if that really answered the question.
Is that drain hole always open, obviously?
Yes, yeah, it is always open. Mm-hmm.
Okay, so, all right, my question basically is that how does that affect the actual pressure of the ram air coming in, since there is an exit?
Okay, that's a good question. I'll be honest with you, I don't know the answer to that. So
I always wondered about that through the years. So
okay, yeah, that's a good question. And again, that's honestly not something I even thought about there. I don't know. I'd have to look that up, and I would, if you're here for the next month, I'll get back to you on that. But I'm curious to know that too now. So I will figure that out, and we'll talk about that in the future. Sound good?
Okay.
Okay. All right. You got it. No, that's a very good question. So I'm curious about that too. All right. All right. So where are we here? So we'll get back to the first instrument, right? So we're going to talk about the altimeter first. So basically, this instrument displays the airplane's altitude. It's a certain type of altitude. We'll talk about that later, though. But what's going on here inside the instrument case, we've got a set of what we call aneroid wafers. So these aneroid wafers have an internal pressure of 2 inches of mercury, which is your standard at sea level. And the wafers expand and contract as atmospheric pressure changes, as this is directly hooked up to your static port. So then the wafers are then linked to the dials on the face of your instrument to indicate altitude. So basically, as they're compressed, it'll indicate a decrease in altitude. And as the wafers are expanded, it'll indicate an increase in altitude. So if we kind of take a look at this diagram here in the PHAC as well, here's the inside of the instrument case for the altimeter. We can see the static port directly connects to the instrument case. So here it's all filled with static pressure. That'll either compress or expand the aneroid wafers, which are then mechanically linked to the pointers on the face of the instrument, and you'll get your altitude readouts on there. So if we take a look on the right side, here is the kind of the face of the instrument. So we've got hundreds of feet, thousands of feet, and 10,000. So what we're kind of seeing right now, the reading looks to be 620, 630 feet, somewhere around there. So we've got 5 different types of altitude that you also want to understand here when talking about the altimeter. So the first one is indicated altitude. So this is just whatever is directly read from the altimeter when you have your current altimeter setting in. And the second is true altitude. So this is height above mean sea level. So this is basically, again, what you're reading on the altimeter there, true altitude. Absolute altitude is AGL, right? Height above ground level. So let's think about this. Let's say you have a lesson right now, you're going out, pre-flighting 8 Mile trial, you're sitting in the airplane. What is your true altitude right now on the ramp at Princeton? Does anybody know the answer to that? What's the true altitude going to be?
128.
128. Awesome. All right, you got it, Gab. Now, how about absolute altitude? Okay, all right, Andrew, how about this? What's the absolute altitude going to be then?
0.
0, exactly. We are on the ground, so that'll just be 0. Perfect. All right, so next one is pressure altitude. So I think the book defines it as height above standard datum plane. I never really understood what that meant. It's kind of weird, but it's basically at the datum plane, you've got your standard pressure setting of 299 or 2. In other words, though, let's say you go to your airplane right now and you put in 299 or 2 as the altimeter setting on the altimeter. Whatever you're reading in terms of the altitude there is going to be your pressure altitude. So again, that's pretty important when you are, doing your performance charts in POH. So important to know how to calculate that. Then finally is density altitude. This is pressure altitude corrected for non-standard temperature. So density altitude is directly related to your aircraft's performance, right? So higher density altitude, you're going to have a decrease in performance of your aircraft. So altimeters, pressure sensitive, right? So as we fly from areas of high pressure to low pressure and vice versa, this is going to have a pretty significant effect on your altimeter settings. So we kind of have to always adjust to get an accurate true altitude or MSL altitude reading, right? So a couple ways you can do this while you're flying, right? You've got ASOS, AWOS, you can tune the ATIS. If you're getting flight following from air traffic control, they can provide that to you. Or, if you've got Sentry or Stratus hooked up in the back, you can get your ADS-B weather as well. You would kind of set that right over here in the Closman window. So if you adjust this knob on the lower left of the face of the instrument, you can just set it to the proper altimeter setting. So, if air traffic control said altimeter 299 or 8, you would just rotate this and the little card will move until the dial is centered at 299 or 8. So not a perfect instrument either. There are errors for the altimeter due to non-standard pressure and temperature. So this is important to kind of understand, and I'm going to show you a couple websites to kind of figure this out here. So when we have warmer than standard temperature, your true altitude is actually higher than indicated altitude. So in other words, whatever you're seeing on your altimeter is just a little bit too low, and it's vice versa. So let's say you have a lower than standard temperature now. Your true altitude will be lower than indicated. So again, that means whatever you're seeing on your altimeter is a little bit too high. So now there's also errors due to pressure, right? So let's say, for example, you're going on a cross-country flight flying from an area of high to low pressure, but you do not change your altimeter setting. If that's the case, your true altitude is lower than indicated. So again, whatever you're seeing on the altimeter is too high. To remember this, if you remember the phrase high to low, look out below, that's going to kind of help you remember what's going on there. And then for flying from low to high pressure without adjusting your altimeter setting, your true altitude will be higher than indicated there. So again, whatever you're seeing on the altimeter is too low. That's kind of confusing to understand when you're just looking at the words, but there's this guy, he has a website that's pretty good to learn a lot of different topics actually, but he's got these 2 simulators you can kind of play with this. So this first one is for altimeter errors. So you can kind of like type in different altitudes, pressure settings, temperatures, and kind of see the effects of, the non-standard temperature and pressure errors. And the second one is just an altimeter itself. So kind of playing around with the different altimeter settings, see what changes. Like you figure out that a 1/10 of an inch, 0.1 inch of mercury of pressure will translate to 100 feet of altitude there, for example. So pretty good resource there. This guy has a bunch of other things too. I think I've probably linked something else of his, maybe like a VOR simulator or something like that. But I definitely recommend kind of playing around with the tools he has available. All right, so that is the altimeter. And your next pitot-static instrument we'll talk about is the vertical speed indicator. So this instrument measures the vertical speed of the aircraft in terms of feet per minute. So in other words, you're answering the question, are we climbing, descending, or in level flight? So inside our instrument case, we've got something called a diaphragm, which is a flexible metal container. This unit is directly connected to the static port. And since our static port is measuring just your outside static atmospheric pressure, that means that the pressure inside the diaphragm will match the atmospheric pressure outside. So very similar to the aneroid wafers in the altimeter, the diaphragm here will expand and contract as atmospheric pressure changes, basically as we climb and descend. So the instrument case also has a direct static line, so it's also being filled with static pressure, but there's one difference here. It's actually vented through a tiny hole we call a calibrated leak. This actually causes the pressure inside of the case to change more slowly than the pressure inside the diaphragm. So if we take a look at this little image here, also from the PHAC to kind of understand this. So here's your instrument case for the VSI. This is your diaphragm that's going to expand and contract. You can see there's a static line that goes directly into the diaphragm. So this immediately reacts to static pressure. The instrument case itself is also filled with static pressure. So however, there's a calibrated leak. So that little tiny hole will cause the pressure here to change slower compared to the diaphragm where it's more immediate. So if we kind of apply this to a scenario, let's say we're putting the airplane in a climb, right? We're gaining altitude. As we climb, we know that our atmospheric pressure will decrease. So static pressure is decreasing. Since the diaphragm is directly linked to your static port, that means that the air pressure in the diaphragm will immediately decrease. The instrument case, right? For the instrument case, the pressure in the case is also decreasing, but it's decreasing at a slower rate due to that calibrated leak, the little tiny hole. So this is now momentarily basically going to result in the case having a little bit of a higher air pressure than the pressure in the diaphragm. So in other words, you've got a pressure differential now. So now that you got this difference in pressure, the higher pressure will then squeeze the diaphragm, and then the diaphragm is mechanically linked to the pointer of the face on the instrument, and you'll not indicate a climb, right? And it's the exact opposite for a descent, basically. And if you have a greater pressure differential, the needle will then indicate a higher climb or descent rate. So that's the VSI. And the last one we'll talk about is the airspeed indicator, right? So as we mentioned earlier, I think it was Umar who pointed it out, this is the only instrument that uses both the information from your pitot tube and the static port. So the pitot tube measures ram air pressure. So ram air pressure, the faster the airplane travels, the greater the ram pressure is. So this ram air entering the pitot tube gets directly sent into the airspeed indicator. And just like the VSI, there's a little diaphragm inside the instrument case that it's sent into. And similar concept, right? The greater the pressure, the more the diaphragm will expand. So as the diaphragm will expand, that'll be linked to your airspeed indicator needle, and you show an increase in airspeed. So the explanation that we just covered really only talked about the pitot tube, but we were just saying this uses information from both the pitot tube and the static port. So let's kind of figure out where this comes into play now. Where is the static port? So the key thing we have to remember here is pressure changes with altitude, right? As we're climbing and descending, atmospheric pressure is also changing. So if we don't take this into account, then the airspeed indicator would actually indicate different speeds at all different altitudes, even if we're just traveling the exact same speed there. So to fix this problem, we've got the static port that's going to connect and fill the instrument case with static air. So this subtracts out the static air pressure from the ram pressure from the pitot tube, and we've got something called dynamic pressure. So dynamic pressure is ram air pressure minus static pressure, and that's directly converted into airspeed. So basically, in other words, how does the airspeed indicator work? We're just subtracting ram air pressure minus static pressure, and that gets you dynamic pressure for airspeed. So here's what it looks like on the inside again of the instrument case, and all these good diagrams found in the PHAC chapter 8, which is the flight instruments. So as you can see, here's the pitot tube. Ram air from the pitot tube is directly sent into the diaphragm, which expands and contracts, and then the static air line is actually going into your instrument case. So the diaphragm is filled with the ram air from the pitot tube, and the instrument case itself is filled with the static air pressure. So we're basically taking the difference from those two and getting airspeed there. So just like different types of altitudes, there's different types of airspeeds as well we want to talk about. So simplest one is indicated airspeed. This is whatever's on your airspeed indicator, pretty basic to understand there. Calibrated airspeed. So this is indicated airspeed corrected for instrument or position errors. So if we look at, I think it's, section 5 of the POH, your performance charts in the 172R, the first chart is going to be an airspeed calibration chart to convert your indicated to calibrated. So that's going to be pretty useful there when you're doing your cross-country planning and all that. The third one, not really too important for us, but it does exist. Equivalent airspeed. So equivalent airspeed is calibrated airspeed. corrected for something called compressibility error. That really only exists when you're flying 180, 200 knots plus, and in our 172Rs, we are not doing that, so we don't have to really worry about that there. So true airspeed, however, this is actual airspeed or actual speed through the air, right? I think another definition is calibrated airspeed corrected for altitude or knots under temp. And then finally, ground speed. This is actual speed of the aircraft over the ground. So in other words, true airspeed adjusted for any wind conditions, right? If you got a headwind or tailwind, their ground speed will be a little slower or faster, as we've seen. So when you look at an airspeed indicator, right, you've got the needle and you've got different airspeeds, 40, 60, 80, and all that. But it's a little bit more than that. We've got a color-coded marking system for different airspeed limitations on the instrument, actually. So we're talking about all your different aircraft V speeds, VFE, VNO, all that kind of stuff. You're actually going to be able to figure out where that is on your airspeed indicator. Not every V speed is on there, though. So you're not going to see maneuvering speed, VA, right? That changes with weight. You're not going to see VX or VY, best rate and best angle of climb. You're not going to see your landing gear operating, standing speeds there. All that, you can find that in your POH. But definitely, let's take a look at this airspeed indicator over here. This is whatever you see in your 172R, right? And this table on the bottom will show kind of what each part of the color-coded system will indicate. So we'll start with the top here. This first wide arc is your flap operating range. The bottom of the wide arc, the lower limit here, is your VS0, your stall speed and landing configuration. And the upper limit of the wide arc is going to be VFE, maximum flap extension speed over there. The green arc, this is your normal operating range. And let's also talk about the limits, right? So your lower limit of the green arc is VS1, stall speed and specified or clean configuration. And VNO is the border over here, the green and yellow. That's going to be your maximum structural cruise speed. Yellow arc is your caution range, so you only should be operating there in smooth air. So it's bumpy, slow down. And finally, the red line is your VNE, never exceed speed. So if you exceed that, you're probably going to have some kind of structural failure. So does anybody know what some of these speeds are on the 172R? It's like, what is VNO in the 172R? Does anybody know? All right, it's going to be 129 knots. Oh, did someone about to say it? Okay, all right. VNE, does anybody know what VNE is going to be in the 172R? So you can also kind of take a look at the airspeed indicator that may would help.
163?
Cool, all right. I think that was, I heard two people. I think that was Umar, 163. That is correct there, awesome. But yeah, you can find all the different airspeeds again in your POH there. Cool. So let's also talk about blockage of the system. This is definitely something that will come up when you're studying for your private check ride. Good to know as well. So whenever you have errors with these instruments, this is almost always going to indicate either blockage of the pitot tube and or the static port, obviously. A couple of different reasons for blockage, right? It could be moisture, water, ice, like we talked about, dirt, or insects. So like over here, this pitot tube, there is a wasp hanging out in the opening over there. So too bad for you. Also, so how do we prevent this? So during your pre-flight, make sure that you remove your pitot tube cover. You don't want to be like this over here, and also check your pitot and static port openings just to make sure that they're unobstructed over there. So I was kind of thinking about this. The blocked pitot tube would only affect the airspeed indicator, right? We know the pitot tube only hooks up to that instrument, so it's only going to affect the airspeed indicator. So I'm curious to see if anybody knows the answer to some of these questions here. So what happens when the pitot tube is blocked, but the drain hole is open? So again, the pitot tube, the front is blocked, but the drain hole is open. Does anybody know what's going to happen there to the airspeed indicator?
It would be a static air.
Right, so you're only going to get static, right? So what's going to happen is the airspeed indicator will actually just drop to 0 over there. So airspeed is going to go right to 0. Cool. So now let's take the next scenario. Let's say both the pitot tube and the drain hole are blocked for something further in the system that's blocked. What's going to happen to the airspeed indicator? Anybody know?
It could stick at a certain speed depending on when it blocked.
Okay, all right. So I think that one is actually what we're going to talk about next with the static port. So what's going to happen is, maybe you're kind of on the right track. I'll show you what it is actually. So it'll kind of act like an altimeter actually. So what happens is, let's say you climb, you'll see an increase in the airspeed. and when you descend, it'll kind of decrease a little bit. So you're basically getting unreliable indications. So basically, though, once you verify that one of these is happening, blockage is suspected, consider using the pitot heat, right? They may be an isoform or something in or around the tube there. But if it's a wasp and you're flying, too bad for you. All right. So here's what it kind of looks like, though, in a diagram. So these are both found in the PHAC, right? So 8-9 is if the pitot tube is blocked, but the drain hole is open, right? Airspeed is just going to drop to 0. However, if both of those are blocked, like the pitot tube and the drain hole is blocked, something in the line itself, the airspeed indicator will kind of act like an altimeter, right? So just like we were talking about, if we climb, it'll increase a little bit, and if we descend, it'll decrease a little bit. So you're basically getting pretty unreliable indications there. So now, what about the static port blockage, right? So the static port's hooked up to all 3 of those pitot-static instruments, so it will affect all 3. So first, we'll answer the question, what happens to the airspeed indicator? So this is what I think, Andrew, you were answering a little earlier here. So if you maintain the same altitude at which the blockage occurred, it'll indicate correctly, so that'll be good. If you climb, though, the airspeed will indicate lower than it should, and then if you descend, the airspeed indicator will indicate too high. Does anybody know what will happen to the altimeter? What will happen to the altimeter here if the static port is blocked?
Is that where it freezes?
There you go, exactly. That'll just freeze at whatever altitude the blockage occurred. You got it, Andy. And how about the VSI? What is going to happen to the vertical speed indicator if the static port is blocked? All right, so the VSI will freeze at 0, actually. So that's what's going to happen. So taking a look at this diagram again, blocked static system, some kind of blockage in the tubing there. Frozen altimeter, the VSI has a constant 0 indication, and your airspeed indicator will be inaccurate, right? All right, so that's the blockage there. So once you verify this happens, just like Andrew was talking about earlier, like he got it, we've got the alternate static source, right? So after you verify that a blockage has occurred, use that alternate static source. So if you pull out that little knob under the throttle there, we're now getting static pressure from inside the cabin. So it's actually measuring a bit of a lower static pressure. And because of that, your instruments may be just a little bit off. So like we talked about earlier, the airspeed indicator will actually indicate just a little faster than it should. And there's that calibration chart in the POH that you can check for to see what the error is going to be. It's not too bad. Altimeter will indicate just a little bit higher, and the VSI will momentarily show a climb. So I think it's on the interior checklist. One of the items is alternate static, right? What you can do, just make sure it's pushed in. But if you pull it out, you're going to see the VSI flickers up momentarily, and your altimeter just indicates just a few feet higher there. All right, so that brings me to the end of the pitot-static system. So we're now going to go into the gyroscopic flight instruments now. So each one of these instruments, yeah. All right, what's up, Andrew?
Why is it not on the regular checklist? That seems like something that you would want to check.
Which one?
The alternate static.
That's a good question. Do you mean what's the regular checklist?
I mean the placard, the plastic laminated one. That one doesn't tell you.
Okay.
That.
So it is on there in the interior checklist. So the interior,
right.
So that placard that we use in the airplane, the checkmate checklist, the bottom left is the interior checklist. It starts with, passenger brief, hops, tack time, circuit breakers, and then there's alternate static right there. So it's like one of the last 1 or 2 items there on the interior checklist.
I don't remember it either, actually.
Yeah, I thought it said circuit breakers.
What are we supposed to do? Are we supposed to pull it out, and how do we check it?
Good question. So I see some students, they'll just verify that it's pushed in. I do like to pull it out there. So when you pull out the alt static, you just verify again, mainly these 2 on the bottom here. The VSI will momentarily show a climb, so it'll flicker up a little bit. And the altimeter will indicate just a little bit higher. And then when you push it back in, that'll reverse, and you're getting external static pressure. So that's what I'm usually checking for. I'm 99% sure it is on that placard that we use in the airplane. I'll have to double check. But I'm pretty sure I usually do that with my students. But yeah, I'm thinking it's on the bottom left, the interior checklist, those couple items. It's not in the start. I know it's not in the start there. It's in the interior there where the passenger brief is. I'll check tomorrow and we'll figure that out.
I'm pretty sure it's there only because I know I do it. The alternate static. It's the only thing I'm like, I've done that every time. And in one of the planes, it's really stiff.
5-4 uniform. Yeah, it's very hard to move in 5-4 uniform. Exactly. So, yeah, and it's a little better now, actually. So it's not as bad, but maybe a couple months ago, I was like impossible to get that.
Literally, I was like, alternate static, guess we're going to break the glass.
Yeah, exactly. There you go. So hopefully that kind of answers your question. But yeah, it's a good thing to kind of check for it. All right, so yeah, getting into the gyroscopic flight instruments now. So each one of these instruments relies upon a gyroscope to function, and the gyro is either driven by air from the vacuum system or electricity. So does anybody know what are the 3 gyroscopic instruments out of our standard 6-pack? All right, so on here, it's going to be the remaining 3. So we've got the attitude indicator, the heading indicator, and the turn coordinator. So all of these have gyroscopes in them that are functioning inside. So before we're going to talk about each instrument, let's just actually review what a gyroscope is and how it works. So a gyro is basically a heavily weighted spinning disc that can maintain its orientation and position. So there's 2 important principles we want to talk about with the gyroscope. I'm curious, does anybody know the 2 principles of a gyroscope might have been mentioned? Probably not. Let's see. Okay. So I'm thinking of 2 other ones right now. Let's see. Is Umar alive? I think I was talking to you a little bit about this earlier. Let's see. All right, so let's go over anyway. So
There's
these 2 principles.
Precession?
Yeah, there we go. So one of them is precession. You got it. So precession. And the other one is what we call rigidity and space. So rigidity and space and precession. These are 2 principles of a gyro that are very important to kind of understand to figure out what these instruments actually do. So rigidity in space is basically saying, let's say we are spinning a gyro. It's going to remain in a fixed position in the plane which it's spinning in. So if you move it around, the position of the gyro is basically not going to change. So I'll kind of show you a visual representation after that. And then the second one, precession. This is a little bit harder to understand, but again, I'll kind of show a diagram here. So let's say you've got a spinning gyro, right? And we apply some kind of force to it. The gyro is actually not going to respond or feel the force there. It'll feel the force 90 degrees ahead from the original point in the direction of rotation. So that can definitely cause the instrument to have some unwanted errors, especially your heading indicator, right? All that drifting. So we'll talk about that later. But here's a visual representation of those 2 principles. So the one on the left here is rigidity in space. So as you can see, the gyro is spinning, and even though it's kind of being thrown around here, the position of the base is changing, the gyro just remains in that fixed position. So it's rigid in space. And then the second principle is precession over here. This diagram's kind of weird, but the gyro is spinning this way to the right. And if you apply the force here on top, it'll actually feel at 90 degrees ahead of in the direction of rotation over here. So for all of these gyroscopic instruments to work, they have to be really spinning at a very high speed. And as we were talking about earlier, the instruments can either be powered by the vacuum system or electricity. They all could be powered by vacuum or electricity if they wanted to, but for backup safety reasons, different instruments are powered by different sources. So if one of them fails, you still got another source there. So does anybody know what spins the gyros and the attitude indicator, heading indicator, and turn coordinator? So we know it's either vacuum system or electricity. Does anybody know?
Vacuum.
All right, so vacuum system for which of these instruments?
Heading indicator, maybe?
All right, cool. So yeah, the heading indicator, that's powered by the vacuum system. How about the attitude indicator?
I think it's all 3. Or vacuum.
All right, so the at least in our airplane for that we're talking about the 172, the attitude and heading indicator are going to be powered by the vacuum system, and our turn coordinator actually is going to be powered by the electrical system there. Some turn coordinators actually will see like DC like on the face of the instrument to tell you that it's electrical system. But yeah, again, could be different. So that's at least what we have for our airplane there. So attitude and heading indicator is the vacuum system, and then turn coordinator is powered by the electrical system. So Something that really important to understand here, the spinning of the gyros with air is not accomplished by blowing air. So we're not blowing air through it, we're actually sucking air around it. So the vacuum system, right, it's providing suction that's necessary to operate those two instruments. So basically, you find more detail about the vacuum system in your POH, of course, section 7. But basically, we've got 2 vacuum pumps that are connected and powered by the engine, and they're drawing filtered air from the cabin through your instruments, which allows it to spin the gyros. So this diagram here comes directly from the POH, so we can kind of take a look. There's your 2 engine-driven vacuum pumps and the vacuum system air filter drawing air from the cabin, sucking the air through all your instruments and the vacuum gauge and all the way out your overboard vents. All right, so let's get into the instruments itself. So attitude indicator, we'll talk about that one first. This informs the pilot of the orientation or attitude of the aircraft relative to the Earth. So in other words, the artificial horizon, right? This is the sky, and you got the ground over there. It indicates pitch, which is the fore and aft tilt of the instrument. And you've got bank or roll, right, which is the side-to-side tilt. And let's see here, we've got an artificial horizon bar in the middle, that white bar, and you've got a miniature airplane. And by those 2 components, we can basically depict the position of the airplane in relation to your true horizon. So, you're flying VFR, clear skies, beautiful day. Is the attitude indicator useful? Not really, but, certain conditions it is, right? Instrument flying, of course, night flight, poor visibility, or if the horizon is kind of hazy out there, obscured by clouds, can be somewhat useful instrument there. So when we read this, there's like these tick marks on the outer rim that indicate different bank angles. So 0, 10, 20, 30, 60, and 90-degree angles of bank. So when you guys are, doing your private steep turns, 45-degree steep turns, that's right in between these 2 markings over there. And then for degrees of pitch, they're located above and below your artificial horizon. So, and this one looks to be in 5-degree increments there. So it looks like we're pitched up about somewhere between 5 and 10 degrees there. And then this triangle on the top of the instrument will indicate your correct bank angle. So here, bank angle is 0, your wings are level. So again, if you want more practice, kind of reading the attitude indicator, you can find this stuff in the PHAC as well, or go on the airplane. But for example, this one on the left indicates a climb left bank, maybe 30 degrees, and it's pitched up about 5 degrees there. So inside the instrument case, of course, you got that gyro, and here it's mounted on a horizontal plane. This operates based on that principle of rigidity in space, which is just saying that gyro is fixed and it will remain in that horizontal plane as the airplane is pitched and banking all around. So that allows it to basically indicate the correct attitude of the airplane. So the limits of the instrument, so your bank limits are between anywhere 100, 110 degrees, pitch limits between 60 and 70 degrees. So if somehow you're exceeding those limits, the gyro will tumble and spill and you're gonna get all these weird readings. So a couple errors you wanna be aware of here with the attitude indicator. When you accelerate, it may show a very slight pitch up, and as you decelerate, it may show a slight pitch down. And when you're rolling out of a 180-degree turn, it could actually indicate a slight turn to the opposite direction there. So we'll talk about the heading indicator now. So this senses the airplane's movements and displays heading based on your 360-degree compass rose, and you've got 5-degree increments over here. And the little markings are labeled every 30 degrees with that final 0 emitted. So over here is like a 330 heading. Maybe some of you can guess just by looking at this picture where I got that from based on the missing knob on the heading indicator bug. So something important to understand here with the heading indicator that I've seen a lot of confusion about. This instrument really, there's no built-in heading sensing ability. It actually only reflects changes in heading. So it cannot detect heading by itself. We actually always have to align to something. So if you want accurate readings, we have to constantly realign that instrument to the correct heading by referencing your magnetic compass, right? So to accomplish this, we push in that little knob on the lower left side and twist the instrument. Sometimes a little bit difficult on some airplanes, but sometimes work a little easier there. You'll be able to align that properly with your magnetic compass. So the principle is pretty similar here, right? Just like the attitude indicator, this instrument also operates based on rigidity in space. But the difference here is the gyro is mounted on a vertical plane, which is then connected to that compass card in the face of the instrument, right? And again, due to rigidity in space, as we turn the airplane, the compass card will hold that same position relative to the vertical plane, and you'll have accurate changes in heading to be shown. So here's what it looks like on the inside, right? The difference is the gyro is mounted on a vertical plane there, but again, it's still connected to the compass card on the face. All right, so very similar limits, right? Same limits with the pitch and bank. And if you exceed those, gyro is going to spill, you're going to have incorrect readings. But the primary error here with the heading indicator is precession, right? Due to friction and precession, as we all have seen, the heading indicator will slowly drift away from your correct heading. Another factor on the amount of drift is going to be the condition of the instrument, right? So what we have to do, we have to constantly recalibrate it with the magnetic compass throughout flight if you want accurate indications. Just be careful about doing this. You know, when you want to make sure you're straight and level on accelerated flight, nice and smooth, so your magnetic compass is giving you accurate readings as well. So finally, let's talk about the turn coordinator. So this instrument is used while banking to indicate both direction and rate of turn. And let's say, you have a vacuum system failure. This could be used as a backup source of bank information, because then your attitude indicator would fail, right? So the emitting aircraft in the center would indicate the direction and rate of turn the airplane is currently in. So we've got 2 tick marks on the outer rim. So these are for wings level. And over here, left and right, that's for your standard rate turn. So a standard rate turn is basically you're turning 3 degrees every second, or 2 minutes to complete a full 360-degree circle there. So below that airplane, we've got an inclinometer or your slip skid indicator. So all it is, you got a tube that's filled with kerosene and there's a ball in it. And this ball just freely moves left and right in response to whatever the aerodynamic forces push and pull it. So ideally, when you're flying right, you want the ball to be in the center, which means that your airplane is coordinated. But if the forces are unbalanced, the ball will slide left or right, which will either indicate a slip or a skid. So if we take a look at this over here, we've got 2 different diagrams or 2 examples of turn coordinators, one on the left, one on the right. Which is a skid and which is a slip? Does anybody know the answer here? All right, so let's figure this out. So let me, I'll click this. There we go. So on the left, we have a slipping turn, and on the right, we've got a skid. So let's kind of talk about this in more detail, figure out what the difference is. So a slip is when the ball is on the inside of the turn, so you don't have enough rate of turn for that in bank. And the opposite for a skid, that's when the ball is on the outside of the turn here. So you've got too much rate of turn for the amount of bank, right? So a good way to think about it is if you kind of look at your turn coordinator and think of the ball as your tail, that can help you kind of picture if you're in a slip or a skid there. I'm sure we've all heard the term step on the ball there, so you can use that to assist there.
Would the slip be for like a slip to landing?
Okay, that's a good question. So it's kind of this, it's all the same concept, right? But like kind of what we're talking about here, let's say you're turning an airplane, but it's not coordinated between your ailerons and rudder. We're just trying to think of it as a slipping turn or a skidding turn. But yeah, that's basically the same kind of concept. The difference here we were talking about earlier, right? The attitude and heading indicator, that's based on your vacuum system. Turn coordinator, however, that relies on your electrical system to spin the gyro. Additionally, this operates based on precession. So that's the other difference there. So if we take a look, here's the inside of turn coordinator, or better yet, got one over here, thanks to Ken. Oh, wait, no, how am I going to show this with the background? Oh, man. Okay, let's see. Well, it's not there. Oh, too bad. Let's see, how do we do this? All right, I don't even know if I can change the settings. Let's see. All right, well, maybe I'll just have to, all right, we'll just kind of look at this picture then here. Same kind of stuff. So here's your gyro inside there. It's kind of slanted about 30 degrees. But yeah, this is just mainly operating based on precession is the key to understand there. And then the ball is just a tube filled with kerosene. All right, let's see. Okay, so that's kind of the end of the content I had there. So if anybody has any further questions, we can kind of discuss now. But then if we have some additional time, I did have some written test questions or just kind of some questions to go over as well related to these topics. So does anybody have any further questions here? Let's see.
I have a couple. I popped in chat earlier as well, but
all right, let me take a look. All right, Umar said, would it be possible for a prop wash to affect the readings in the pitot tube, or is the tube placed far enough on the wing so that such an effect would be negligible? Yeah, that's a good question too. So again, it's placed there, so you're not going to have to worry about that effect. Also, would the attitude indicator and the G5 also run based on a gyro? Okay. I don't really fly 3 of November too often, so I'm not 100% sure. Yeah, so I'll get back to on that, Umar. Let's see. I'm trying to think here. Probably does. I don't have the G5 in front of me here. Anybody know the answer to that? Maybe anyone have like advanced avionics in their airplane?
I'm asking Ken.
Okay, he actually showed me one earlier, so I'm not 100% sure. My guess is yes. I don't know.
It's based on it is a gyro inside of it. Yes.
So the attitude indicator in the G5 would also be based on a gyro.
Yeah. Yeah.
Yeah.
Okay, there you go, Umar.
Okay, cool. Thank you.
You got it. All right, so let's see if there's no other questions here. We can proceed then. So we don't have to go through every single one of these, but I've just got a couple like written test questions we can kind of go over together. So some of these are kind of basic, some of them not so much. We can kind of talk about it if needed. So if anybody has the answers, I guess you can say it out loud or put it in the chat, ABC, whatever you guys want to do there. So first question, if the pitot tube and outside static vents become clogged, which instruments will be affected? So let's see here. First option is altimeter, airspeed indicator, or VSI. Second is altimeter, airspeed, and turn slip indicator. And the last one is altimeter, attitude indicator, and turn slip indicator. So does anybody know the answer to this one here?
It would be the first one because turn and slip would be related to the vacuum system, right?
All right, sweet. So yeah, it would be the first one there, right? Altimeter, airspeed, vertical speed, that's all your pitot-static instruments. Yeah, the turn coordinator, that's all your gyroscopic stuff, right? Cool. All right, so there's your answer. Second question, to receive accurate indications during flight from a heading indicator, the instrument must be either set prior to flight on a known heading, calibrated on a compass rose at regular intervals, or periodically realigned with a magnetic compass as the gyro precesses.
Last answer.
Last answer, you got it. Exactly, Andrew. So that's going to be correct there. We periodically have to realign that. So someone could say, oh, it's the first one, which we do. We do set it on a known heading on the ground. But if you don't do anything after that, you're not going to get accurate indications for sure. All right, so question 3, what is an important airspeed limitation that is not color-coded on airspeed indicators? So, we kind of talked about the color coding system, but not every V-speed is going to be shown on there. So does anybody know which one of these is not indicated on the airspeed indicator?
Maneuvering speed.
All right, you got it, Sandro. Yes, the maneuvering speed is not coded there. Never exceed speed is your red line, and maximum structural cruising speed, VNO, is the border of the green and the yellow arc. All right. So question 4, static pressure, also known as ambient pressure, is present only when an aircraft is in motion, always present whether an aircraft is moving or at rest, or is never present when the aircraft is in motion. What is this?
Always.
Always present.
All right, good. Always present. That one's pretty self-explanatory there. So yeah, static pressure is always present, no matter if we're moving or at rest. Good. So another airspeed indicator question here, right? So as we talked about, the airspeed indicator has various color markings. The green arc is it's either speeds that should only be flown in smooth air, normal operating range, or the full flap operating range.
Normal operating range.
All right, you got it again, Sandra. Yeah, so normal operating range of the airplane is your green arc there. All right, so this is going to relate to some of that altimeter errors we were talking about. So if a flight is made from an area of high pressure into an area of lower pressure without the altimeter setting being adjusted, the altimeter will indicate it's either higher than the actual altitude above sea level, or the actual altitude above sea level, or lower. So which one is this going to be here?
High to low, look out below is what you said, right?
There you go, Andrew. You got it.
Yeah.
All right, awesome. Yeah, so high to low, look out below. So the altimeter is going to indicate too high. So we're higher than what we actually are above sea level. You got it. All right, so here's an airspeed indicator. What is the caution range of this airplane? So you've got 3 different choices. What's the caution range?
I think they're 165 to 208.
You got it, Omar, exactly. So 165 to 208, that's going to be the yellow arc is your caution range. Sounds good. All right, so another kind of definition-based question. What is true altitude? So 3 different definitions, true altitude.
Is it the sea level one?
It is the sea level one, yeah. So perfect, you guys got it exactly. So true altitude is the vertical distance of the aircraft above sea level. So true altitude is MSL. So there's 2 other definitions here, right? Bonus points. Does anybody know what the other 2 definitions are for? So how about the top one? Vertical distance of the aircraft above the surface. What's that one?
AGL?
All right, I didn't understand that.
Absolutely.
Try that again. All right, there you go.
ASL?
Cool. All right, I heard it once. I heard absolute altitude. That is correct. Okay. Now, how about the last one? The height above the standard datum plane. What is that?
Pressure altitude.
Okay, there we go. Yeah, that's pressure altitude. Again, a couple of different definitions of pressure altitude, but you know, in a written exam, that's what you're gonna want to see there. Standard datum plane. Cool. All right. So next question here. So there's an attitude indicator. How should a pilot determine the direction of bank from an attitude indicator, just as the one illustrated?
It sounds like the second one. This is kind of confusing me, though.
Yeah, it's a weird question. It's a weird question. Yep. So looking at this, it's a little bit odd. So, you know, the key word to understand here is this: just asking direction of bank. So it is going to be that second one, the relationship of the airplane to the horizon bar here. And this, when I was looking at this, I was like, oh, it's going to be the last one, right? You know, looking at A, okay, there's my bank angle. But again, I wasn't reading the question carefully enough. It's direction of banks. They're not really asking for, you know, bank angle. So correct. All right. So under what condition is pressure altitude and density altitude the same value? So this depends on if you know what both of those are in their relationship.
Standard temperature.
All right, you got it. At standard temperature, right? Because density altitude is pressure altitude corrected for non-standard temperature. So if it's standard temperature, they're going to be the exact same value. You got it. All right, so under what condition will true altitude be lower than indicated altitude? So this has to do with those altimeter errors we were talking about earlier as well.
That colder than standard air?
Yeah, there you go, Andrew. Exactly. So colder than standard air temperature. Seems like we got all these altimeter errors pretty down. Awesome. All right. So let's see here. It's kind of an interesting question to consider. So altimeter setting is the value to which the barometric pressure scale of the altimeter is set, so that the altimeter indicates you got either true altitude, calibrated altitude, or absolute altitude. So what are we actually looking for in the altimeter?
We want to know how high we are above the ground, right?
All right.
That calibrated altitude at the field elevation.
All right. So they're trying to actually trick us with this one here, right? So there's such thing. We have the calibrated airspeed. That's something. So they're trying to throw us off in that sense. So it wouldn't be the calibrated altitude there. So we don't have a definition for that one. So it would either be true or absolute altitude. So again, this depends on if we kind of understand the definition of each of those.
Would it be true? Because like, if it was absolute, we'd set it to 0.
There you go. Exactly. You know, if we find different spots, if it was absolute, we just keep setting that as 0, which is not obviously what we do. So you got it. We were setting true altitude, right? True altitude. Perfect.
So Wes, what was calibrated altitude? Is there such a thing as calibrated altitude?
There isn't. That's the tricky part of this one there. Yeah. They were trying to throw us off there. There's such thing as calibrated airspeed. So that's why they're trying to get that in our mind. But yeah, it's going to be true altitude. All right. So airspeed indicator, which color identifies the power off stalling speed in specified configuration?
Lower limit of the green arc.
All right, you got it, Gab. So the lower limit of the green arc is your VS1, stall speed and specified configuration. What about VS0? What is that on the airspeed indicator? Anybody know? That's your stall speed and landing configuration.
Bottom of the white arc.
You got it, Andrew. Bottom of the white arc. Awesome. All right, so let's see if anybody knows this one too. So let's say we have an altimeter, current setting is 2915, but we change that to 2985. What altitude change is going to occur there?
700-foot increase.
All right, perfect, Sandra. Yeah, so it's going to be a 700-foot increase in indicated altitude. 0.1 is going to be equal to 100 feet. So if we go up 0.7, that'll be your 700-foot increase. Awesome. All right, and the last one I've got here for you guys, I think we had a similar question earlier. Now, let's say if we have a flight made from an area of low pressure into an area of high pressure without adjusting the altimeter setting, what's going to happen there with the altimeter?
Yeah.
Yeah, letter B.
Letter B, yes, letter B.
Yeah.
Okay, there you go. Yep. Yeah, letter B, second one. Yeah, the altimeter will indicate lower than your actual true altitude above sea level. All right, sounds good. You guys did a pretty good job with all these questions there. That can definitely print your written. Nice. So I just have like 2 additional resources just to mention here. So I kept mentioning this earlier.
One question on the white line. Why do they not indicate the 110 speed in the Cessna, but only the 85?
So that's a good question. VFE, there's two VFEs, right, for your plane. The 172 are 110 for the first 10 degrees and 85 for the second and 20 and 30 degrees, right? They'll probably be thinking it's kind of impossible to indicate that there. So they had to just put for the 85. So we just kind of have to remember that 110 is for the first notch only, because the white arc is your flap operating range. I don't know. That's kind of the best I can explain it. They just kind of can't figure out how to properly display that. I know most airplanes will just have one VFE, and that's kind of easy to explain it there because it's just a white arc. But we do have 2 to remember. So that's kind of the best I can explain it there. It's just, I don't know how they're going to figure out how to display that on a normal airspeed indicator. All right, so 2 resources that I've been mentioning. So obviously, PHAC Chapter 8 is all about flight instruments. So if you read this, you will learn a lot more. So I only covered a couple of things, but there's a lot of different subjects within this chapter that'll help you with your understanding there. And of course, your POH, right? Section 7 is all about your systems. So anything you're wondering about your airplane, you can probably find it in your POH. And if not, there's tons of other resources out there. So yeah, it's pretty much all I've got for you guys there. Thank you very much for listening as always and attending the Zoom session. So does anybody have any further questions that want to discuss?
Well, thank you very much for the presentation. This has been a very, very, very good memory jogger for me.
All right, I appreciate it, Alex. I'm glad it's been useful for you. Thank you for coming.
Excellent.
Thank you.
This has been super helpful. Thanks, Wesley.
All right, I appreciate everybody. Thank you, Andrew. Thanks, Sandra. Thanks, Umar. You guys got it, of course.
Okay, over and out. Have a good night.
Good night.
All right, have a good night.
All right.
Well, thank you, Wesley.
You got it, of course, Gab.